3. That is a Magnus effect. Magnus effect. Magnus effect. That is what is Magnus effect? There is a dynamic lift due to spinning ball. When the ball is spinning, even we are discussing seeing the cricket. Okay, there is fast ball. There is no balls. There is no turning. Whereas in the rough, there is only no bounce on it. There is no turning. Whereas during spin ball, the ball is takes the deviation. That is it takes curved path, which is lifted by certain amount of force. That is called as dynamic lift. So here Magnus effect. So the dynamic lift due to spinning ball, that is called as it's a Magnus effect. Magnus is studied on this spinning of the ball. Then he was given the graph Magnus effect. What is Magnus effect? The dynamic lift which is acting when a ball is spin, that is called as Magnus effect. This dynamic lift is useful in graph when aeroplane is taking off, the graph take off. In this case, which is lifting the aeroplane with a certain amount of upward force. That is called as a dynamic lift. The dynamic lift is here working. This of magnetic effect. Okay, so we are discussing here. Okay, so I'm taking A is a magnetic fluid. It is flowing streamline flow. The velocity of the molecule is the same. So this is the velocity of the stream of the air. So the air is flowing. That is horizontally. This is streamline flow. When the ball is without spin, that means which is moving faster. That means fast moving. Okay, then what's happening here? I make this a ball. This object has a ball, cricket ball. This object has a cricket ball. Okay, the ball has a top of this ball and the bottom of the ball will both have velocity. I'm taking velocity of the ball is at the bottom, at top VB, and at the bottom there something has a VB. Okay, so here the direction of the A, that is velocity is same, and the direction of the ball at top I'm taking VB, both are same. At top, resultant velocity V are equal to resultant velocity at the top, that is V plus and that as VB, because the stream has flowing like this only, and this velocity of the ball at top is both are the same direction. I'm taking this resultant velocity at the top of the ball. At the bottom, at bottom, the resultant velocity I'm taking as V are equal to at bottom. Okay, the string has moving with the velocity V. Okay, V plus at the bottom also the ball has velocity VB. Okay, I'm taking as this, I'm taking as VB. So from the velocity of the ball at top is equal to the velocity of the ball at the bottom, both are same only. And the ball is moving in the rough stream. When the ball is moving in the rough stream, the velocity at the resultant velocity at top and resultant velocity at the bottom is the same. Now we are discussing second case. Okay, and the ball is now here rotates, that means spinning. So we discuss it here. Now, when the ball is rotates here, the object has this is a ball. So here, this object has it is a rough surface. It is a rough surface. The ball has some rough surface. Okay, the ball has some amount of rough surface. So here the ball is spinning. The top of this ball velocity object has VB. Okay, and bottom is taken as velocity object has VB. Okay, which is a spinning arm, which is a spinning. Now this ball is flowing the base in the rough stream. So this object has stream. This is moving with velocity V. Okay, this object has a stream. Now this ball is spinning in the rough fluid. Okay, so this object has spinning. This is object. This is a rough surface. This object has a rough surface. So this is object ball. The ball is now rotating. The ball is now here rotating. So at this velocity object has VB. At this object has velocity object has VB. Okay. Now here we can find out the resultant velocity at top and bottom. We can find out. Okay. At top, resultant velocity object has V R equal to velocity of the stream plus. So the ball has direction. The stream has direction. This direction. The ball has a direction. Both are the same direction. Object has a VB. This is the residual velocity at about top of the ball. Now take here at the bottom. At this bottom, and take here. At this bottom, the residual velocity take here. So we are equal to velocity of the stream. Velocity of the stream is moving. That is horizontally. Velocity of the vector is v. So at the bottom, the ball has moving. That is ready with velocity v, which is opposite to the stream flow. The base of it is v minus of and it is vb. The base here residual velocity is less. Residual velocity is here more. Okay. Here residual velocity is more. Here residual velocity is less. There is a velocity difference at the top and the bottom of the ball. So then due to that, here velocity is more. Here what's the difference? Corresponding pressure is here less. Here velocity is less. Corresponding pressure is more. So at the bottom of the ball is pressure is more, at top of the ball is pressure is less. Due to pressure difference, top and bottom, the ball is now lifted up. That is called as a dynamic lift. So the dynamic lift, which is acting on the spinning ball, which is called as a Magnus effect. So that's why during the spinning, the ball is it is lifted up towards the wickets, okay, which is not bounce, which is deviates from its path towards the wickets. Okay, this is called as a Magnus effect. And the same principle is applicable to this is aeroplane wing also. Okay, same the diameter. Okay, Magnus effect is applicable to this wing of the aeroplane. So, when the aeroplane is on off runway, which is initial rest position, so which is not take off. So here, when the engine starts, then the flight, the airplane is moving on the runway. When it is moving, so you can check it here. The wing of the airplane is constructed in a specific design. That is a curved shape. The top of this face of this wing of this aeroplane is look like a curved shape. You can observe carefully if you are going to travel the flight journey, and then you can observe the wing of the aeroplane is a curved shape. So here this is a curved shape. Which is on the runway. When it is moving slowly, then what's happened? The aeroplane is moving on the stream, which is air. Okay, this is stream. This is as a stream. It is traveling on the rock stream, which is fastly moving, running, slowly. The speed is increased, gradually its speed increases. At a certain particular value, the pilot is lifting this aeroplane. So here, Bernoullis principle is applicable. Okay, certain lift, dynamic lift is sufficient to build up, then the pilot is take off this aeroplane into sky. Okay, so what's happening here? Okay, the top of this wing has a curved shape. So here this is the speed has velocity is v. Okay, so this is a curved shape has taken. So the top is velocity is more. Pressure is more. Pressure is less. At the bottom of this inner side of this wing, so velocity is here, velocity is less here, pressure is more. At the same time, at this wing also. At the top of this wing has velocity is more, red velocity which is exposing to more velocity, and pressure is corresponding, pressure is here less. So the curved side inside pressure is velocity is here, velocity is less, corresponding pressure is more. There is a pressure difference in and out of the wing, and this wing and this wing. So there is a lift which is acting up, then it is called as a dynamic lift, which is lifting the this flight. At that moment, when the dynamic lift sufficient to build, at this case, the pilot is lifted up this flight. This is also applicable of Bernoullis principle. This is called as a dynamic lift. And one more applications of the Bernoullis principle, we can observe it. During the summer, the wind storms coming. This roof of this house. Okay, this roof of the house. Okay, during in the summer, the wind storms come. The wind is blowing with great speed. So this wind, okay, this velocity has more. Velocity is more. At the top, velocity is more. Velocity of the wind is more. Corresponding pressure is less. Inside, velocity is less. Pressure is more. There is a pressure difference. This atmospheric pressure only. This is also pressure. This is pressure. So there is a pressure difference in and out. Then what's happened here? The roof is blown off. The base, there is a pressure difference in and out. Then the roof of this house that is moved away. This is also application of the Bernoullis principle. And one more general example. Okay, this is a calendar which is hanging to the roof walls. And the fan is fixed. What's happened? The pages are flee away from the rough stick of the wall, from the rough wall. They are flee away. What is the reason here also? Here also we can explain this case applying to Bernoullis principle. What's happened here? The top face of this page is on the calendar, which is exposed to the velocity, great velocity, which is applied to great velocity. So here velocity is more, pressure is here, less, pressure is less, right? And inside of this paper, inside of this page, so what's happened here? Velocity is less, corresponding pressure is more. So there is a pressure difference top and inside of this calendar. Then what's happened? The calendar is lifting up. This is called as dynamic lift. Same dynamic lift applicable to the wing of the aeroplane and the spinning ball. Okay, there is a difference in the pressure of the top of the page and inside of the page. Here, velocity is exposing, velocity is coming. So this is a low velocity. Velocity is more, pressure is less. Inside of this page, what's happening? Velocity is less, pressure is here more. Corresponding pressure difference between this top and the inside, then the pages are lifted up. This is also a dynamic lift. Okay, these are the applications of Bernoullis principle. Okay, first we are discussing about which one here, speed of efflux. Okay, then after next one we are discussing Venturi repeater. Third one we are discussing which one? Third one we are discussing here Magnus effect. These all are the applications of Bernoullis principle. Okay, thank you.